Okay, so first I would like to thank the organizers and the Cirm staff for allowing this conference to hold, this virtual conference, and especially to give me the opportunity to give this talk in 3 parts. So this series of lecture concerns the descriptions of some special class of Codimension foliations, namely Codimension foliations with pseudo-effective conormal bundle. So before giving any statement or giving any definitions of the terms involved in this title, I would like to introduce the general setting. So we are going to deal with holomorphic distributions. So these objects, we will call D, are determined by a current subshift, TD, of the tangent shift to manifold X, such that TD is saturated, or equivalently that Tx over TD is torsion-free. So these saturation conditions means that we have eliminated fake singularities in codimension 1. And there is a locus where the quotient Tx over TD, which is somehow the geometric normal bundle, the distributions, is not free, locally free, and we call this set the singular locus of D. And this saturation conditions implies that the codimensions of the singular locus is greater or equal to 2. Okay. So alternatively, we can define distributions of the kernel of a twisted non-trivial Q form, so twisted by a line bundle L, and say that a local vector field belong to is tangent to the distributions if the contractions of theta by X is equal to 0. We have also to pay attention that conversely, twisted Q form not necessarily define distributions of codimension Q. So typically take, say, a hyperkähler manifold, dimension 4, and a symplectic 2 form. So the kernel of this symplectic 2 form is reduced to 0, of course. So to define the foliations of codimension 4, which is the foliation by points on the manifold. Nevertheless, it is always possible to define the codimension Q distributions by a twist Q form simply by contracting forms of top degree by the determinant bundle of the tangent shift, the distributions. We are especially interested in global distributions, or involutive distributions, and we have the following theorem or definitions depending on whether you are on the algebraic geometer or not. So that is D is a foliation, is shift of D is involutive, which means that it's stable by Lie bracket. If you're an algebraic geometer, you can take this as a definitions, but it's often the case, indeed. If you are a more traditional geometer, that is Frobenius theorem. In any case, we have partitions of X, or the complement of the singular locus of D in X equals, which are maximal integrals of manifold. Okay, this is tangent of these distributions. So we have an object with dynamical flavor, because if we have leaves, we have, for instance, Taylor group holonomy, which gives a general very complicated transverse structure to these foliations, and so on. Okay, so here I will focus on the Codimension 1 case. That is the distributions of rank n-1. Namely, it is determined by twisted one form. And we can suppose that this form does not vanish in Codimension 1, corresponds to the saturation conditions. And in other words, this is the corresponds to the datum of invertible subsheaf of the sheaf of the contortion sheaf, which we call the conormal sheaf, which plays a prominent role in this talk. And in more layman terms, Codimension 1 distribution is defined by collections of one form, which glue together according to a cocycle GUV, which represents the dual of the conormal sheaf, which is coincide with the geometric normal sheaf, that is the quotient of the Tx by Td outside the singular locus, but not over the singular locus, because I recall that the geometric normal sheaf is not locally free over the singular locus. And in the Codimension 1 case, the integrability properties, the evolutiveness property translate very simply as theta wedge d theta equal to 0. And yes, I have an additional remark concerning these relations, because recall that theta is a twisted one form in general. So the operator d is not well defined, but there is something which makes sense, which is namely theta wedge d theta, because of the derivative rules. So if we derivate dg theta, it gives dg wedge theta plus g d theta. So when taking the wedge product, the factor dg wedge theta is eliminated. We are left with g carry g squared, sorry, theta wedge d theta. So this means that the wedge product is well defined as a twist free form with values in L star to the power 2. Well, L is a line bundle L star is its dual. I consider directly this is dual for convenience. Okay, so take an elementary example. Says area OD, where these integral effective divisors. In this case, theta is nothing but holomorphic global one form vanishing at D. And when the ambient manifold is a compact Keller, well known that these distributions defined by this form is integrable, and in fact, more precise results, which says that this form is automatically closed, and prove quite instructive for the sequence. Indeed, very simple. It mainly makes use of Stokes' theorem. So it goes as follows. You consider a Keller form. So it is positive by definitions. It's in particular, it's from the real viewpoint, it's a symplectic form. And when you consider the real volume form obtained by taking the derivative of theta wedge d theta bar wedge omega to the power n minus 2. And it's sufficient to observe that, of course, this form omega is exact and also non-negative, because the derivative is precisely d theta wedge d theta bar wedge omega to the power n minus 2. So we integrate a form which is both exact and positive. Of course, it forces omega to be 0. So d theta bar is equal to 0. Of course, d theta equals 0. Okay. So you can notice that the case of compact surfaces, the use of the form is irrelevant because n minus 2 is equal to 0. So we obtain in this case that every holomorphic one form in the compact complex surfaces, whatever it is closed. And following the same principle, one can show that every n minus 1 holomorphic form on the n complex compact manifold is declosed. So one can also make the additional remarks that so consider projective manifolds and, with Codimension 1 distribution D. So there are cases where the conormal bundle cannot be effective. For instance, if X is rationally connected, this can occur for the simple reasons that the conormal effective implies that the distribution is given by genuine holomorphic one form, and it is well known that on rationally connected manifolds there doesn't exist such form. Same things when the Picard group of X is reduced to Z. This forces the conormal bundle to be negative, or particularly anti-ample, because if the conormal bundle is positive, this also means that the distribution is given by a one form, contradicts the fact that the Picard group is discrete. Okay, so now I would like to mention some interesting non-integrable examples of Codimension distributions. These letters are provided by contact manifolds, which are odd dimensional manifold. And what is the contact form on it? It's twisted from theta, which verifies these non-integrability conditions, namely theta wedge d theta to the power m does not vanish somewhere. And this is a kind of maximal non-integrability conditions. And so this is quite the opposite of the integrability case, that is Codimension 1 foliations. And there are natural manifolds which carry naturally such structures, namely the projectivized hyperplane bundles. If one prefers the projectivizations of cotangent bundle of a given manifold Y, and the contact structure is somehow tautological on it. So take a point Y in capital Y, say, and a point of X between bracket in the fiber of Y. So X between bracket is by definition the class of a linear form on the tangent space at Y. So we define the contact distributions by declaring what are the vector which are tangent to these distributions, and such a vector will be tangent. It's V. So is its projections by pi lies in the kernel of X. So the kernel of X is well defined, depends, indeed it depends only on the class of X. It's the same if one multiply X by non-zero scalar. Okay, so this define hyperplane distributions. One can verify that it is a contact structure. An alternative way to see this is to consider the standard Liouville form on the cotangent bundle. The Liouville form whose differential, I recall, gives the standard symplectic structure of the cotangent bundle. This Liouville form, this Liouville one form, descends for homogeneity reasons to the P t equal y, but not as a genuine one form, but as a twisted one form, so namely twisted by O1, that is the dual of the tautological bundle. Okay. And actually, there is a strong interplay between symplectic structure, lives in even dimensions, and contact structure, which lives in odd dimensions. But I will not discuss in further details these aspects here. So we have seen previously that Codimension one distributions defined by holomorphic one form is automatically integrable on compact Kähler manifolds. Situations with the conormal sheaf is of the form OD, where these effective divisors, which is the vanishing divisors of the one form, which defines these distributions. And it's natural to ask whether this integrability property still holds if one wakens the positivity properties of the conormal sheaf. And it turns out that the answer is affirmative, following the theorem by Demailly. So this is the following theorem of Demailly, which stipulates the following, that X is still a compact Kähler manifolds. And suppose we have holomorphic sections, but say holomorphic P form, so twisted by line bundle L, L star, whose dual L is pseudo-effective. Then we can conclude that the distribution defined by the kernel of theta is involutive. In fact, I will use this result for holomorphic one forms, but the results for all for every degree. Okay, and yes, so I will not recall fully what pseudo-effective means. Just say that when bundle is pseudo-effective, it's a Chern class, can be represented by the closed positive 1-1 current, and this means also that L admits metrics which can be a priori singular, such as the curvature, which is defined as a current of this metric, is non-negative. Okay. So, in other words, this means that this curvature current admits a local potential phi here, which is only locally defined pleurisubharmonic functions, which is called the local weight of the metric. So I will not do a background of on currents. So if you are not very comfortable with this notion, you can think as a current as a form with distributional coefficients. and as positive 1-1 current as a 1-1 positive forms. Okay, but with coefficients are measured instead of genuine functions. And the remarks that in the case, the standard case where the conormal is OD, with this form can be regarded as holomorphic global one form. This corresponds to the fact that the T, the curvature current, can be taken equal to the D between brackets, which means the integration current along D is a particular case. And as we will see in the sequence, the interest of the Naive's proof is not only the integrability results, but indeed it provides further variable informations, like for instance the existence of an invariant holonomy invariant transverse measure for the foliations, which indeed looks like as a transverse Riemannian matrix. Okay, so I also refer to the Mailly's paper. There is a very elementary and both elementary and elegant corollary of these results, which is the following: that if you consider odd-dimensional Kähler manifold, which admits context structures, that's canonical and bundle cannot be pseudo-effective. And if it is not pseudo-effective, it clearly implies that colored dimensions of the manifold is equal to minus infinity. So if you don't know what is exactly what is the colored dimension, I will do some review on it in the second lecture. And how to prove this corollary? It's very simple, as I said. So consider a contact form, okay, theta. And okay, so from the contact structure, one inherits forms of third degree, which is twisted by L star to the power m plus 1. So a twisted form of top degree, which is nowhere vanishing. So that it exactly means that the canonical bundle of the manifold can be identified with L to the power n plus 1. But this canonical bundle cannot be pseudo-effective, okay? Because the same thing will hold for L. Indeed, if L is pseudo-effective, this is equivalent to say that any positive power of L is pseudo-effective by definitions. Okay, so and if L is pseudo-effective, this will imply, in fact, that theta is integrable, okay, but it is incompatible with the contact structure, of course. And there is also, one can also derive another result. Well, if we combine the Mailly theorem with previous results, one can infer that if one deals with a contact projective manifold, such the second Betti number is greater or equal to 2, then it implies that X is indeed projectivized hyperplane bundle, which carries, we have seen it, a natural contact structure. I guess that term should hold, but for a compact Kähler manifold, but I think it is still a conjecture. Okay, so now I would like to go into details, the proof of the Maillet theorem. So I put proof in quotes, and I will explain why later. So we're going to explain the proof for twisted one form, but this is there is no real difference for any for form of any degree. So the object that we consider is the form theta, twisted by one form theta, twisted by a line bundle, with dual is pseudo-effective, L star, L is pseudo-effective. And so in trivializing charts, consider local sections of L is the norm with respect to the metric of these local sections. It reads as the model of xi squared exponential minus phi x, and phi is pleurissobharmonic, and it corresponds to the assumptions of pseudo-effectivity. And so we are particularly interested in the dual norm, L star, read as follow. Here is so you consider a local section xi star, and here it's a xi star. I apologize for this. I have forgotten the star. So as every when bundle equipped with a matrix, we have a chain connections attached to the H star, and L star. And this chain connections decomposes as a 1-0 part, the H stars, and the 0-1 part, so compatible with the complex structure, D bar, usual D bar. And it is well known that there is an actions of these connections on the twisted PQ form, and which express locally as df equal, with respect to phi, is equal df, so normal d, plus d phi wedge f. And one, as usual, one has sesquilinear pairing between form twisted by L star. So for the non-twisted case, this is consists simply to take two form FG and consider the wedge products of F with G bar. Okay. So in the twisted case, there is an analogous constructions. So this pairing sends a pair of twisted forms to a genuine form. Okay. And the local expressions, if F with G bar, we have to take into account the coefficients arising from the matrix, which is here exponential phi. And these connections, as any metric connections, vector bundle is compatible with this pairing, which means that it satisfies the Leibniz rule, which is written here. Now, we use that theta is our theta is holomorphic one form, so that its d bar vanished. So from this identity, one can derive the following: it is the differential of the something between braces is equal to these pairings of these forms dh star theta with itself, so it gives rise to a positive form, plus the terms between braces involving the curvature of H stars. And so I can easily explicit these terms, and one can, and if one combines this with the use of Stokes theorem, namely says that the integral of this term wedge omega, omega is a Keller form to the power n minus 2 is equal to 0. So we get the following identity. So the terms corresponding to the curvature term is the integration current T of the conormal bundle. Okay. Well, in fact, this identity holds whatever the metric is. Okay. But in our case, recall that T is positive current. So we have an equality between integral of these terms, okay, and both are positive, okay, because of the positivity of the current. So I can derive that both terms under the integrals vanish, particularly this one vanish, and the vanishing property reads at as saying that the theta is closed with respect to the chain connections, okay? Which reads locally as saying that d theta inside with partial d theta is equal to minus d phi wedge d theta, okay? And when forms the wedge product theta wedge d theta, of course, it automatically implies that theta define an integrable distributions. So I put proof in quotes because, of course, you have to be cautious. Yeah. So the reason is that the current T is not necessarily a regular object because pluralized harmonic functions in general are not are far from being regular. But they still can make sense, and I refer to Demaï's paper to justify this, this equality. So as I say that, and we will exploit it for later use, that integrability is a consequence of the fact that theta is closed with respect to the connections related to the metric. Okay. So this leaves valuable information on the, particular on the standard structure of the foliations that we have obtained. So we will see that later. And we can remark that one recovers the decloseness of one form, L is trivial, okay, because these connections coincide with the usual operator D in this case. So, and I would like to conclude this first lecture by two results where the Demaïs theorem play an important role. The first result is concerns Beauville's conjecture. Some 20 years ago, Arnaud Beauville has conjectured that the splitting property of the tangent bundle of a compact Taylor manifold should have a global counterpart, which means that these decompositions of the torsion sheaf, which is of infinitesimal nature, should correspond to global decompositions, not of the manifold itself, of course, but of its universal covering. And with Marco e Bonella and Georges Pereira, we have proved in 2006 that it holds, that is conjecture holds when the tangent bundle is totally decomposable. This means that the tangent bundle splits as the sum of line bundles. And in this case, this implies that the universal covering is isomorphic to a product of curves. Okay. So on this topic, there were previous results of Beauville in the case of surfaces, also of Stéphane Druel in the projective situations. So I will not give any further explanations on the proof of the theorem. But besides de Mailly's integrability theorem, there are also important results of Marco Brunella, which plays a prominent role, namely the leafwise pleurisy-harmonic variations of the point métrique on the leaves. And I'm going to end up with last applications of the Mailly theorem, which is generalizations of theorem by Rosenlich. I will state in the end. Well, it's not completely logical, but so the statement is the following: it's a result that we have obtained with Lore and Pereira. Well, indeed, it was available from 2011, but it was published in 2018. So consider compact Kähler manifolds with pseudo-effective conormal bundle, and consider non-trivial contravariant tensor field, that is non-trivial sections of the antisymmetric power of the tangent bundles. Then the fact that the canonical bundle pseudo-effective implies that V is nowhere vanishing. Okay. So it is worth mentioning that when X is projective, there is a result of very fundamental for Buxom, de Mailly, Paul, and Peternel, which stipulates that, which relates non-unirolness of projective manifold and the pseudo-effectivity of the canonical bundle, namely the fact that X is non-uniral implies that the canonical bundle is pseudo-effective. Okay. Well, in fact, this is an equivalence, but the converse sense is quite obvious. Okay, so what is the theorem of Rosenlich that I mentioned? The following that was an old theorem, or maybe I don't know, I don't have a precise date in mind, but theorem from the 60s. He said that if one has on a projective manifold vector field, non-trivial vector field, and this vector field vanishes somewhere, that then X is uniral. Well, maybe I've forgotten to define what is uniral for a manifold. It means that manifold is covered by rational curve. That is, through every point of this manifold, there is a rational curve passing. And if one has in mind the characterizations of unirolness or non-unirolness in terms of pseudo-effectivity, Rosenlich theorem can be reformulated as follows. That is, consider a projective manifold with pseudo-effective canonical bundle. Then, and consider on it a vector field, which is non-identically zero, then this vector field never vanished. Okay. So we have generalized this result to any antisymmetric power. And as far as I know, the conjecture is remains widely open for general contravariant tensor field. That is for sections of tensor power tangent bundle. Okay, so I have finished with my first lecture. So in order to conclude, would say that my approach is somehow complementary to that of Demailly. So Demailly has proven its integrability result to derive non-existence results, namely non-existence of context structure of a non-uniworld manifold. So my aim is to assume that such foliations exist, such foliations with pseudo-effective conormal bundle exists, and to describe it as precisely as possible. So in the second lecture, I will make some classical review on foliation given by holomorphic one form, and so present examples where the conormal is pseudo-effective with that the foliation is not given by holomorphic one form, and I will also state the main theorem. Thank you for your attention.